Hello again. Let's look at this example. The fourth root of 1250 x to the 10th. Now we want the biggest power of 4 that will still be a factor of 1250, and that would be 625. So we got 625 x to the, x to the 8th, because now I want the biggest multiple of 4 that is less than 10, and that's 8. So I break up 10 into 8 plus 2, namely x to the 8th times x squared. So, and I break up 1250. I take out the 625 that I want, and now of course 1250 is 625 times 2. Now I'm putting the stuff that can't come outside over here and the stuff that can over here. Now I do the honest to goodness fourth root of 625. I get 5, and I do 8 divided by 4, and I get 2 right here, and then times the stuff that can't come out right here. So there's that. Let's go to this next example. The square root of 6x times the square root of 12x. Now that's the square root of we're assuming all variables are positive throughout this video, by the way, as always. So that's a square root of 72x squared. Now I take a 2 out of 72x squared, and I get 36x squared times 2. The whole point is 36x squared is a perfect square. It comes out as 6x, and so I get 6x times the square root of 2. Again, all variables are positive, as always. So there's 6x radical 2. And now, but here's another point of view. Most of you would probably rather do it this way. This is probably the smartest way to do it. But if you like to take things apart piece by piece, here's something for you. Here's method 2. The same problem, radical 6x times radical 12x. You can break up the numbers into product of primes. The 6 is 2 times 3. You can break this up as the 6 is radical 2. Radical 6 is radical 2 times radical 3. And then we got this x right here. So there's radical 6x can be thought of as radical 2 times radical 3 times radical x. And then radical times, now radical 12 can be thought of as radical 2 times radical 2 times radical 3. And then the x right there gives another radical x. Some of you may not like this, but I'm chunking everything down to x's and primes. Now the problem continues down here. That's kind of sloppy. Let me see if I can move that down. There we go. That's better. So now this radical 2 here is going to bump into this radical 2 here and give me 2. Now I've got this third radical 2, and now it's just going to stay radical 2. There's nobody else for it to go with. Another point of view, by commutativity and associativity, you can just combine these radical 2's multiplicatively, that is, and get this 2 right here, and this radical 2 just comes down here. Either way, they're the same point of view. And then now this radical 3 here and this radical 3 here multiply to ordinary 3. And there's no more radical 3's around, or 3's for that matter. And then I got a radical x here and a radical x here. And you know what, guys? I messed up, didn't I? So, oops. Sorry about that. So I've got 2 radical x's, but that just gives me ordinary x. So I'm going to go ahead and cut to the chase. Radical x times radical x, that's just x himself. I'm assuming all variables are positive. Okay, so what we've really got now, 2 radical 2, usually I like to write it that way, but this time I'm going to insert that times sign in between them like that. 2 rad 2 was correct, but I'm going to put that times sign there just for the time being. So I've got 2 times radical 2 times 3 times x, so I can multiply this 2 times the 3, and I get 6. 6 times x is 6x. 6x times the radical 2 is 6x radical 2. This is all being times together. The 6, the x, and the radical 2. Okay, and by radical I mean square root. So there's all that. And now let's look at this one. Radical 8x times radical 2x, that's radical 16x squared, but that's a perfect 4x, okay? All variables positive as always. Now radical 8x squared times radical 2x, that's radical 16x cubed. Now we want to take an x off, and we get 16x squared times x inside here, but that 16, so I break that. Some students like to skip this step and just jump straight to here, but I did this step here. So I break this up, radical 16x squared times radical x, but that's just 4x radical x. Again, we're assuming all variables are positive. So there's that. Now, let's do something else though. Let's say I got radical 8x squared times just ordinary radical x without the 2 there. So that's radical 8x cubed. You break that up. The biggest perfect square that'll go into 8 is 4. So in particular, we want 4x squared. So we do radical 4x squared times 2x. But so we break it up, radical 4x squared times radical 2x, which is just, and that radical 4x squared is just 2x. And this radical 2x here doesn't change. It's just this guy here. Some students like to just go ahead and take out the 4x squared as 2x, and they jump from here. They go from this guy here straight to this guy here. But if you like this step here, that's fine. Just do what you feel comfortable with. Okay. Now here's another point of view. Now this is breaking things up into pieces a little bit. This one is probably for most of you. Most of you probably prefer this first way, but let's look at the second way. Radical 8x squared times radical x, that's radical 8 times radical x squared times radical x. Okay, well, we can break up radical 8. The biggest perfect square that cuts into 8 is 4, so radical 4 times radical 2. And then, but now radical x squared, that's just, and really what's going on is I've got x times radical x, but I'm just writing it like that, shorthand, okay? But the whole point of doing radical 4 was to turn it in, so I can just juxtapose. This is just 2 radical 2 here, and so I got 2 radical 2 times x radical x. But I can just, but these, I can use communities. This 2 times x comes together as 2x. This radical 2 and radical x comes together as radical 2x, like that. I think it's healthy to know how to do this second problem. You may not want to do it this way in general, but it's good to know how to do this. And we're assuming x is positive as always. But yeah, I recommend knowing the logic behind this guy, even if you don't want to necessarily do it when you do the problem. This way is up here is much more economical. But anyway, let's look at this, like the square root of 80 xy squared z cubed a to the fourth b to the fifth c to the sixth. We've already done one like this. We're just doing the square root. Anytime you do the square root, there's a hidden index of 2 that you can't see. I don't know why mathematicians chose it to be that way. I wish they'd put the 2 up there, but oh well. Now the biggest, we don't want perfect cube or perfect fourth order. We just want the perfect square, the perfect order 2. So the biggest perfect square that goes into 80 is 16. We're doing a square root, not a cube root or fourth root, obviously. So we want 16. As it turns out, 16 is a fourth root, but that's beside the point. We're not doing fourth roots here. So the biggest perfect square that goes into 80 is 16. Now, x to the 1. Notice that this understood 1 is smaller than this understood 2 out here. So x can't go anywhere. So we're just going to go ahead and put him in the junk bin. And really, it's not the junk bin. He's crucial. I'm going to notice that 80 is 16 times 5. I go ahead and put the 5 over here, and I put the x to the 1 over here. The things that can't come out are going over here to the right. Now, y squared is going to come out as y, so 2 is even. So if you're even, I'll leave you alone. If you're a multiple of 2, I'll leave you alone. Now, 3, the biggest even number lower than 3 is 2. So I write 3 is 2 plus 1. I break it. I put a z squared here in this pile, a z to the 1 in this pile. And then a to the fourth, I leave it alone. It's even. It comes out as a squared because you do 4 here divided by this index of 2 here, and you get 2 again. And actually, here's the y that came out. If you want to go ahead and cheat and look down below, here's 4yza squared that came out. Now there's a z that stayed in, remember, on account of this z here. When z squared comes out, you do 2 divided by 2 is 1. When y squared comes out, this 2 divided by this 2 is 1. You always divide by the index. Okay, so 16, square root of 16 is 4. Y squared comes out as y. All variables are positive. Z squared comes out as z. A to the fourth comes out as a squared. B to the fourth comes out as b squared. Now c to the sixth comes out as c cubed. You do 6 divided by this 2 is 3. Okay, and then this residue stays inside. Again, you just, like for A, we're done. For C, we're done. Now for B, we want the biggest even number, multiple of 2, that is smaller than 5, and that would be b to the fourth. Okay, and you get the idea. And you take this stuff out. The square root of 16 is 4. The 5 can't come out, and so on and so forth. It's just like we did with those cube root and fourth root examples, except we're just doing order 2, or the square root, which is the second root. It'd be good if they put this little 2 here and here, but oh well. And here for that matter. Oh well. Now here's the cube root. This time, of course, the good news of the cube root, you can actually see the little bitty 3. So the cube root, we want the biggest perfect cube that goes into this guy now. Now it's not 16 anymore. 16 is not a perfect cube. It's a perfect 4th power and it's a perfect square, but it's not a perfect cube. I guess you can't win them all. The biggest perfect cube that goes into 80 is 8. Namely, 2 times 2 times 2 is 8. And the cube root of 8 is 2. So, but anyway, now, again, x to the 1 can't come out at all. Y squared can't come out. Y squared is not as lucky this time because 2 is smaller than 3. So x, y squared go in the recycle bin, and so does 10. Remember, 80 is 8. We want to filter out that 8, so we get 8 times 10. But the 8's the perfect cube. He needs to be over here in the good pile. The 10 can't come out. He's over here in the recycle pile. So we get 10x and the y squared. The x, y squared are not going anywhere. Now the z cubed, now he comes out as a perfect z right here. Okay, because this 3 divided by this 3 is 1. Now a to the 4th, the biggest, we're looking for multiples of 3, not multiples of 2 now. The biggest multiple of 3 that is smaller than 4 is 3 itself. So we want, we break this a to the 4th up is a cubed times a to the 1. We put the a to the 1 in the recycle pile, and the a cubed we put in the takeout pile. And then likewise for b5, 3 is the biggest, so we write it as 3 plus 2. B cubed is in the takeout pile. B squared is in the recycle pile. Now c to 6 is good to go. It's a complete takeout. We do 6 divided by 3 is 2, and we come out of c squared right here. So let's look at, but let me not get ahead of myself. So we got 8, and we had all this times all this in the recycle pile. Now the cube root of 8 is 2. Now remember, you do the honest cube root of 8, but then for the exponents you divide by 3. Z cubed becomes z when it comes out. A cubed becomes a when it comes out. B cubed becomes b when it comes out. Now c to the 6, 6 divided by 3 is 2. It's c squared when it comes out. And then times the cube root of the stuff that could not come out at all. Okay, so there's that. And this is just a good thing to know how to do, okay? So let's move on to other stuff. The square root of 1 over 25, that's radical 1 over radical 25, that's just 1/5. That's pretty unexciting. The square root of 8 over 50, that doesn't look very doable. But notice, now, here it was good to come apart. Down here it's good to come together. We want to come together, that's radical 8 over 50, that's radical 4 over 25, and that's going to be 2/5. Okay, and there's that. And if I didn't point this out, we're always assuming all variables are positive. So back when I did this example a minute ago, suffice it to say all these variables are positive here and up here. With the cube root, it didn't really matter, but with the square root that I did, it would matter. But let's just assume it's positive through and through. All letters that you'll see are positive. So let's just get that out of our hair. I think I said that before, but I want to reiterate that. Okay, so radical 8 over 50, that's radical 8/50. That reduces to 4/25. Now guys, then you just do this square root, but then you can refragment. And let me insert that step. If you get it, you probably don't care. But so we can refragment as rad 25 down here, rad 4 up here. But these are perfect. See, 4 over 25, they're perfect squares. Square root of 4 is 2. The square root of 25 is 5. And 2/5. We're done. This didn't look doable, but it was actually very doable. There is another approach, but I think this one's pretty good. Another approach you could have done is you could have turned square root of 8 into 2 radical 2, and you could have turned the square root of 50 into 5 radical 2, and you could have canceled the radical 2 up here with the one down here. You can also do it that way, but just whichever one you prefer. They're both the same equivalent method. I'll show you what I mean if you don't get it. Like what I could do, remember 8 can be thought of as 4 times 2. And 50 can be thought of as 25 times 2. And then, but you remember, you can yank out that, you do the square root, 4 comes out as a 2, square root of 4 is just 2. And 25 comes out as a 5, square root of 25 is 5. But you have 2 rad 2 over 5 rad 2, but these radical 2's will cancel each other and just leave you with 2/5. You know, radical 2 is just a number. It cancels just like anybody else does. So there's that. That's a good approach, and either one approach is about as good as the other between this guy and this guy. So just pick your favorite of these two, okay? But let me move on to this next problem. The square root of 5 divided by the cube root of 5. That's interesting. So that's 5 to the half power over 5 to the 1/3 power. So that's going to be 5 to the power of 1/2 minus 1/3. But hey, 1/2 minus 1/3, that's 1/6 when you get common denominator and all that. That's 5 to the 1/6 power. But remember, by definition, that's the 6th root of 5. That's interesting. The square root of 5 over the cube root of 5 is just the 6th root of 5. That's pretty cool. And notice that'd have been true if I'd have fixed any number. If I would have chosen 7s instead of 5s, if I'd have put a 7 here or a 7 here, I'd have gotten the 6th root of 7. But you get the idea, okay? Now, let's look at this guy here. The square root of 5 times the cube root of 49 over 7. This one doesn't look so good. This is actually already in simplest form. This is actually the best form to have. I'm just wanting to show this off. I'm just wanting you to be able to mechanically go through this process. In general, I like this probably better than I like this guy over here. In calculus textbooks, you'll see like one solutions manual may have this guy right here, the other may have this guy here, and students are like, what's going on? I got this answer. The textbook says it's this answer. They're the same. You just have to have good algebra to see it. So like the square root of 5 times the cube root of 49 over 7, the trick turns, notice it, the cube root of 49 can be fragmented as cube root 7 times cube root 7, and that 7 can be thought of as cube root 7 times cube root 7 times cube root 7 3 times. That's what the cube root does. Like the cube root of a number times the cube root of a number times the cube root of the number just takes you back to the ordinary number. Now, why did I do that though? Notice that by cancellation, this cube root 7 will cancel with this one, and this one will cancel with this one. So you're just left with radical 5 over the cube root of 7. And notice, though, that that's 5 to the half power over 7 to the 1/3 power. And we're still not feeling all that good inside. Let's get common denominator. Notice that we turn 1/2 into 3/6 and 1/3 into 2/6. Okay? That way these denominators here and here match. Okay, but what's so special about that? This 5 to the 3/6 can be thought of as 5 cubed to the 1/6 power. By the law of exponents, if you'd multiply 3 times 1/6 and get 3/6, that would take you back here. Okay, well, of course 3/6 is 1/2. All right, but I'm going the other way. I'm fragmenting this as 5 cubed to the 1/6 power, and I'm fragmenting this guy as 7 squared to the 1/6 power. So that's 100, but 5 cubed is 125, so it's 125 to the 1/6 power, and 7 squared is 49. So we got 49 to the 1/6 power. Now, what was the point of all that? Oh, but notice by definition, well, it's not behaving. This is the 6th root of 125 over the 6th root of 49, but by the come together law of radicals for positives, you can do the 6th root of 125 over 49. If it bothers you that I skipped that step, I'll try to insert it. My computer is not acting all that nicely. So remember, it's just by definition, guys. 49 to the 1/6 power is the 6th root of 49, and 125 to the 1/6 power is the 6th root of, well, 125. Get up there. Okay. So it's the 6th root of 125. And sorry it skipped a line on me, but then it skips a line, it ran out of room, and then you get the 6th root of 125 over 49. But remember by the rules, the 6th root of this over the 6th root of that is just the 6th root of this over that. So the 6th root of this over the 6th root of that is the 6th root of entity this over that. Okay, that's by the rules of radicals. Guys, I'm about out of time. That'll be all for this video. Thank you. Bye-bye.